Well, this is another topic. I'm going to call it Chapter 6, but it's really not in Chapter 6. We first discovered slope fields as far back as Chapter 4 when we were learning how to find the antiderivative. So I'm just going to kind of pile it in here because we didn't spend much time talking about slope fields back then. We're going to do so in a little bit more detail right now because slope fields have become part of the test. I think probably for about the last 15 to 18 years it's been on the AP test. So we want to make sure that we know how not only to create a slope field, but also how to match a slope field with a differential equation. Now, a differential equation, of course, that we've talked about in some detail, is an equation that includes both the function and its derivatives, and the order of the differential equation is the same as that of the equation's highest order derivative. So differential equations, for the most part, we have been dealing with first order or second order differential equations, and we have solved them using a method called the separation of variables. Now, what happens if we get one where it's not easily solved by separating the variables? Now, there are lots and lots of other methods. In fact, those of you guys that are going to become engineers are going to have to take a class called differential equations, where you'll learn, maybe even 2 semesters, where you're learning the different methods to solve differential equations. And I actually had a professor at my college that was one of the first to program computers to solve differential equations. Pretty cool stuff. This is way back in the 70s with personal computers and such when they were first coming out. So when we cannot solve a differential equation by separating the variables, then what we're going to do is we're going to make a sketch of what we call a slope field, which is sometimes called a direction field, which is a visual solution to the differential equation. So first things first, let's look at a definition here. A slope field is a series of short tangent lines drawn at multiple points using the expression from the differential equation. So they're going to give us a differential equation to solve, and we're going to do ones that we could be able to solve in a more traditional method by separating the variables. But we're going to be, in some cases, but we're going to construct a slope field by using the differential equations to find the slopes of the tangent lines that would be to the curve at the points in a region of interest. So normally they'll give you a grid, kind of like they have down here, and they'll give you a differential equation. Now we could solve this one. And they will also, in many cases, give you a point that's on the curve, because the slope field doesn't just give us enough information to find the solution to one particular solution of differential equations, but gives us a family. And in this case, I have 25 points marked on this grid, and here's my differential equation. Once I have drawn the slope field, then I am going to draw, or do my best to draw, a curve that goes to the point 1, 1 right here, that uses my slope field as a direction, kind of like arrows pointing go this way, to come up with the sketch of the function, the actual solution to the differential equation. So first things first, what I want you to do, and it's a pain because I've got 25 points here, but what I want you to do is I want you to take each one of the points one at a time and substitute them into this differential equation. Now this particular differential equation, dy dx equals 2x, is kind of a nice one because there's only one variable, only the variable x. And so you're going to see some patterns. When it just has the variable x, when it just has the variable y, or when it's just a constant, there's certainly some patterns to help us to make the sketch a little bit more efficiently, and also to be able to recognize. So I'll start with this point way out here. This is -2, +2. So I'm going to find dy dx at -2, +2. So I plug the -2 in here for the x, and I get -4. Now what I'm going to draw, or best of my ability, is I'm going to draw a short line here. I'm not going to put the arrows on the ends, but I'm going to draw a short line segment, let's say, that goes through this point, that if I was drawing the line, that would have a slope -4. So it kind of goes up and to the left, but it's a little bit steep, so I'm just going to approximate it like this. Okay, so that if I was to, go down 4/1, I would be on there, or if I go up 4 to the left 1, I would be on this line. And I'm going to do this for 24 more points. Now the good news is, because these all have the same x value, all 5 of these points, and since everything's in terms of x, all of these are going to have slope 4, or excuse me, negative 4. So best I can, I'm going to try to draw these so they all have slope negative 4. Then I'll go to negative 1, positive 2. So dy dx, you can see again how convenient it is that it just has the one variable. If I plug negative 1 in here, I get negative 2. So all these are going to have slope negative 2. So they're a little bit flatter. And then I'm going to plug in 0, positive 2. So dy dx at 0, positive 2 is going to give me 0. Well, that's easy. Those are all going to be horizontal. So they're just going to be little lines like that because they're going to have slope 0. And then I go ahead and I go to, let's say, 1, 2, this point up here. So dy dx at 1, 2 is going to give me 2 times 1, which is 2. So best I can. Now again, since they all, this differential equation only has x, can I get away with this? If it had an x and a y, or if it just had a y, then it's different from top to bottom. They don't all match vertically. And then one more here. Dy dx, let's say 2, 2, which would be positive 4 because you plug the 2 in for the x there. So these are going to be even steeper here. Looks like I have some symmetry with respect to the y-axis here. Now what I want to do is I want to draw the curve that goes to the point 1, negative 1. 1, negative 1 would be right here. So I'm going to try to draw them. They don't have to go through the other points, but I'm going to try to draw them using using the little line segments as like direction and which way to go. So if I start here, as I go to the right, do you see how it gets steeper? So I'm going to start out, it's going to getting steeper and steeper like this. So you see how the slope is like the same as the slope of the tangent line. And here, as I go to the left, it kind of flattens out. And then it kind of looks like it's going to go up and to the left, kind of not real steep at first, but then it's getting steeper and steeper and steeper. And it looks like I have a parabola here. Let's see. Dy dx equals 2x. So dy equals 2x dx. So that means if I integrate both sides, I get y equals x squared plus c. I have the point 1, negative 1. And you can see that very well. So I get c is negative 2. So I have y equals x squared minus 2. Well, there it goes. That's pretty darn close. That turns out to be the curve given this initial condition. Now, otherwise, I have a whole family of graphs because they would move up. It's just a matter of where what x value and y value you're using, but I would have a whole family of graphs here from the slope field. But here I can get a specific curve, and that would be the solution to this differential equation given this information. All right, now, this one was simple enough that I could solve it using integration, but sometimes they integrate nicely and sometimes they don't. So you need to be able to draw these out, and it's going to take practice. You're going to get a few of these to practice here in just a bit when we get to that assignment. But I have some more problems here. And in this example, I have matching. Now, I want you to look at the first problem there. It says dy dx equals 0. That means no matter what point I plug in, dy dx is 0. So that means it's horizontal. Do you see how that matches with all these horizontals here, that this matches with d? And in this case, dy dx, it's also a constant. It's 1. So the slope would be 1 no matter what point. Do you see how that matches nicely there with h? They all have slope 1. And then it gets a little bit more interesting. Here's the 2x one that we just did just a little bit ago. And dy dx equals 2x. Wasn't that looking a little bit like, let's see, what do we have here? It looks a little bit like c here. See how it kind of goes upward? Let's go back and look at our curve. Yeah, it looks a little bit like c there. So this one would be c here. Okay, and then what else do we have? Okay, we have 1/2 x squared. Now, 1/2 x squared, no matter what you plug in for x, it's always going to be positive. And notice here that it doesn't have a y, so the vertical lines should all match. So it's always going to have positive slope. So I'm looking for something that always has positive slope. These all have positive slope, and you see how they all match in the same vertical line? So I would have to say that this one matches up pretty nicely with F. Now this next one here, I think that's x squared there. X squared, yeah, that's an x squared. You just can't see it. It's a bad copy there. And in this case, all my slopes are going to be negative. But they're going to get closer and closer to 0 as x gets bigger. So it starts out here with, let's see, do we all have negative slopes here? Hang on a second, I got to find here. I'll have negative slopes here. Let's see. Well, maybe that's a 3 there, because I don't think I have one that has all negative slopes. So that one will integrate. Yeah, that's going to work out that it matches up here for x is positive. And again, vertical lines would all be the same because it just has an x, it doesn't have a y. In fact, I don't think I have an example that it just has a y. That's my mistake. And so I would have negative 2 over x cubed. Well, it's going to be negative for values of x, negative slope, and positive for negative values of x. So that's going to match up here with answer A. Anyway, you can get the idea here on how this works. So it just takes a little practice to get halfway decent at these. Now, I think I have one here. No, I don't have a good example with an x and a y. I think I have one in your assignment, though. So you just go ahead and you substitute the values in for each point, especially if it has an x and a y, because for every point there's going to be a different x or a different y or both. And you'll go through these, and then you'll make the number line suggestion, the tangent line segments here at each one of the points. So I hope that helps a little bit more. And I'd like for you guys to print out the worksheets and practice on this.